tell you to stop from taking notes. Okay, so there's a big concept here around grouping called rational subgrouping. So I want to sort of describe rational subgrouping a little bit. Subgrouping, it's sort of a weird name. You're like, subgroup of what? It's a subgroup, but what it means is it's a grouping within the data you have, or the bigger group of data you have. You don't have all data, you have a data set. So when we talk about subgrouping, we're talking about some subsets of the data you have, okay? The concept of subgrouping is one of the most important concepts in problem solving and analytics. It's extremely important, can't underemphasize that. Shewart, the guy we talked about with control charts yesterday, he sort of came up with this, well, I don't know if he came up with it, but he really leveraged the concept of classifying things into group and trying to get things that are within the group more similar and the things that are between the groups more different. And leveraging that, we can do some kind of a comparative analysis. So the aim of subgrouping, specifically rational subgrouping, is to include only common causes of variation within subgroups and special causes between. And I'll show you what that means to us in a minute. So skip that for now. I'll ask that question in a minute. So the world of subgroups, here's all our data that we have, data on the table. We're talking here, we have in this diagram 6 subgroups, and each subgroup happens to have a consistent number of data points inside it, 4 data points. So we refer to the subgroup size as K, and the number of points per subgroup is N in this world. So just to understand that, you might see that come up. So there are non-rational subgroups, which are time-based subgroups. I mentioned yesterday, we are not doing statistical process control, but in the universe of statistical process control, you generally do time-based subgroups. So every day we take 5 data points, or every 2 minutes we take 3 data points, or whatever. We have these little rational groups that are time-oriented. We're not doing that. We're doing it based on some difference. We saw a lot of difference examples there. So here's a scenario. Name 2 online shopping resources. Amazon, I knew that was going to be one of them. eBay, okay, Amazon and eBay. So let's call scenario A Amazon, okay, and just talk about Amazon right now. So we're not going to look down here for a minute. Scenario A, we order 3 boxes of, let's call them tennis balls, okay? So they're supposed to be the same diameter, right? Would you like your tennis balls to be the same diameter? But you're a curious sort, so you want to measure your tennis balls. So you open box 1. So I know tennis balls come in a canister of 3, so don't freak out. You open box 1, it's got 4 tennis balls in it, and you record the diameters, and these are overly inflated diameters, so let's just pretend it's trying to visually illustrate. You get 4 different diameters, right? This one's really small, and this one's really big comparatively. You open box B, same thing, 4 different diameters. You open box number 3, 1, 2, and 3, same thing, different diameters. How would you, if you wanted them to improve, you're going on to do your Angry Amazon review now, and you want to suggest an improvement to them because you're helpful, what would you suggest? Does the box matter? So what if these were 3 different brands? Would brand matter? All brands have the same diameter variation issue, right? So in this top scenario, Amazon's problem is not box-to-box variation. The different boxes make no difference in your analysis. It's really ball-to-ball variation, right? Everybody get this concept so far? Let's go to eBay, scenario B. You order 3 boxes. You get this box with 4 balls, this box with 4 balls, this one. And let's say this one here is about the right size. These guys are coming in too big. These guys are coming in too small. And let's say, what would you do on your review on Amazon to help them fix, eBay to help them fix their problem? What is their problem? Is it different than this problem? How? Yeah, boxes are very different, right? So you might say, ooh, you might conclude from this, if these were 3 different suppliers, what do they call them on eBay? Sellers, 3 different sellers. You might say, in the future, I'm going with seller 3. I got the right size diameter balls. But seller 1, I got too big, and seller 2, I got too small, right? So seller, I'm going to select my seller based on that. Could you do that same analysis up here? Could you select a better seller if these were 3 different sellers? No, they all suffer from the same problem. So this concept is a big concept. So what we work here is different than what we work there. Even though we have, if I put all those balls into one bin, we have the same variation problem, right? If I had all 12 of those balls in one bin from Amazon, and I compared that to eBay's 12 balls, there's no difference. But how I would go work this problem in scenario A, I'd say, well, all the sellers or boxes have variation. So box to box, seller to seller makes no difference. Take all the variables around seller or manufacturer or whatever it is on that side, take them out of the equation. They're not important. There's something else going on. But here, now I say, ooh, seller to seller is really different, or box to box, same thing. So now I go investigate that. Do you guys see that? It's a huge clue by knowing, is the variation within the boxes, like this scenario, or is the variation between the boxes, like this scenario? Show of hands if you got the concept. I want to beat you over the head with it pretty hard because we're going to carry it forward. Good. Okay, so now, this is sort of a simplification of the previous page. What I'm showing here is the within variation is greater than the between variation. So the variation inside the boxes is greater than the between. So I'm putting some language around this. And down here, in this eBay scenario, the variation between the boxes is bigger than within. So as an analyst, this is a really useful thing for me because I can go ask different questions, look for different variables, divide the future data in different ways. So you can see that here. This is within box variation. This is more between box variation. So now, I want to ask you some quiz questions, see if you follow along, see if we can add some math to this. So again, still animated on the screen. So I have markers. I'm going to steal these guys. Do I have any more of the? Yes, I'll just use 3 of these. So we all work for Sharpie, okay? Sharpie's been having a problem. Caps have been either falling off or they're too tight to get on. So what happens if a cap falls off a marker as a user? Am I happy with that? Dries out. What if I can't get it on? Am I happy with that? Probably not as big a deal, but it ends up maybe drying it out as well so we're all working for Sharpie. I'm going to show some symbols here. These represent a marker cap diameter. So this is, I measured 5 marker caps of red markers. And I am now saying this one is a smaller diameter, and I go up the list here, and this one is the biggest diameter. So I have 5 different diameters, where the vertical height on the page represents small to large. Everybody with me? Okay, pretty easy. Now, how would I estimate how much variation is inside or within this group? Difference between small and large. So which difference would you calculate, Alex? Or 400? I feel like when I say Alex, the smallest to the largest. What would that attribute or calculation be? The range, right? The smallest to the largest. So I didn't give any answers here, but you guys as a room just told me that if I want to represent the within variation, I'm going to go smallest to the largest as the range. Okay? So remember that. Within variation is range. You told me. I didn't tell you. You told me. Okay? So now, I have more markers. Turns out I have a red production line. I also have a blue, whoops, went too fast, a blue production line, and I have a green, an orange, and a purple, and a yellow production line. And now, these different production lines have different amounts of marker cap variation, true or false? So now, how would I represent the variation between these different production lines or groups? Yeah, so you say, well, on average, this orange one here is high up, and this green one's lower, right? And the purple one's low too, but not as low as the green, etc. So mean, I like that, because that's a very simple way to sort of compare these groups. If I average them and then look at the distance between them, that's how I'm going to look at the differences between groups using averages. You agree? So we said the within variation is is range, and the between variation is average. So memorize that. Within variation is range, between is average. Everybody got that? Okay. So now, here's where the real animation or the real question comes in. So there, you told me that. I didn't tell you this. You told me this. I got to emphasize this because I want you to memorize it. Okay? Now, here's the quiz question. We're working at Sharpie. They want us to fix this problem. They take this data. Here's the data we have. You guys are hiding over there. You should come sit in the middle here. We'll do that at the break. I didn't even see you guys come in. How can I harass you? All right, so here's the scenario. What would you work? Tell me, what would you go fix? Your job now is to fix this problem. Caps are falling off. Caps are not going on. Customers are screaming. We're going to lose our jobs. The company X is going to take over. How would you fix it?
Minimize the range.
Minimize the range. So how much is within one of these or all of them? So what would you work first? Inside one line or between the different lines?
Minimize difference between the averages and range.
Both. So you want to fix everything. What would I do first? Okay, let me change the scenario, make it a little easier for you guys. Yeah? Voice of the customer. So this is not underlined, but there's no voice of the customer here. This is process, but we're going to bring that in this afternoon, so hold that thought. So let's just say we're unhappy with this amount of variation and leave it at that. Okay.
The problem is we don't know which colors cause the problem.
Yeah, so there's probably a lot of, yeah. They should be. All the markers should be the same size. This is cap diameter, so that's a really good question. Is it the marker diameter or is it the cap diameter? That's a really good question. Let's assume that we know it's not the marker diameter for this scenario. Somebody else has done that work. We now know it's this cap diameter that's the problem. And we're seeing this kind of variation. So you guys are asking the right questions. When I have data, I just shouldn't trust. I should have a domain understanding. I should have a process understanding. I should have a customer understanding. All those things we argued for yesterday.
If I'm just looking at the data as we see it right now, I see a bigger problem with between sets than within.
All right, I got to make it easier for you guys. So let me mix this data, put it in a blender. Now, what if somebody came to you with this data? What would you work on? Yeah, means or between, right? Because this yellow has got way bigger diameters than this green, doesn't it? So between colors is a huge source of variation at this time. Let me mix it up, blend it a little bit. What if you had this scenario? What would you work? So Cecilia's telling me, Bill, you got to go work the yellow line. It's got a lot of problems. Should I believe her? Any line will do. That's powerful, right? To say all the lines are suffering from the problem in a sense here. Go work any line to reduce variation. So I made it easier for you. You guys nailed it visually there. Now we go back to our original scenario. We could try to guess all day, but let's just put it on a tool to help us out. You guys up for that? Good. Finally, some enthusiasm. Good, good, good. All right. So we're going to use something called, well, we can use box plots. Let me go through box plot first, and then we're going to use XBAR charts. So box plots, we could actually take the data. Has anybody used a box plot in here? Super simple, right? But here we have comparisons. So here we have machines versus week 1, 2, and 3. So we have machine number 1 and machine number 2. This box plot, it represents sort of where the first quartile, second quartile, third and fourth quartile are and where the median is, right there in the center. So this is a representation of the data for machine 1, week 3. And this is a representation of the data for machine 2, week 1, right here. So where would you work in this scenario, given these simple box plots? Would you work on machine 2? Seems to have low variation relative to machine 1. Would week matter for the different machines? For machine 1? Yeah, it looks like the variation's lower here, mid-level, higher here. So that there's something going on there, and I can start asking questions, what's going on. Simple box plots can be very helpful. So if we had our Sharpie data, I'd want to see it plotted like that. Here's some more examples. This is shale stuff, but variation in drill to put online at the end of the process. So we could say, oh, you know, where should we work in there? Total non-value added or standby, et cetera. So just some examples. I don't want to spend much time on this. We've all seen box plots. But I want to introduce control charts. So what is, XBAR control charts, because we learned IMR control charts yesterday, right? So XBAR is a way to see, and XBAR stands for averages and R stands for ranges, by the way. A way to see where the majority of the variation is between group or within group. Hey, that sounds just like what we were talking about. How do you see it? You take rationally grouped data. We have rationally grouped data. We have marker production lines is our group variable there, right? And then we plot in Minitab using one of these options here. And so you get something like this. Now, this isn't complete. I'll just show some animation here. But all it is this is production line, I forget what my colors were, but red, blue, green, whatever, yellow, orange I think is in the middle, et cetera. So I have my production lines, and I have what I plot here is the average value of that production line, and then the range of data. Those are the things you said you cared about earlier, the average value and the ranges. So simply I measure those things and put them on 2 plots. Super easy. You can do that by hand. Now, what I do is then once I have these ranges, I calculate the average of the ranges, and I get this thing called R bar right here, R bar. Okay? And so that's the average variation inside all the groups, 19 units, whatever the heck that is, okay? Now, I can take that just like I did yesterday and take that R bar and divide it by the constant D2 squared of n, and both those things change by how many variables are inside each subgroup. So if I have a subgroup size of 5, it's going to be a square root of 5 here and the value of D2 for 5 that we look up in a table. And we multiply that. That's our estimate of sigma times 3. So this is the mean of all the averages, the grand average, X double bar, plus 3 sigma. And we use that to calculate these control limits. Everybody follow that? It's the same logic we used yesterday. So I did this R bar, I use my 3 sigma using R bar, and I calculate these control limits. Now, let's think about what that means. You told me, let's see what you told me if I can remember. You told me when I'm looking inside a group, I'm going to think about the variation as the range. So range is within. So we could almost think of this representing the within variation, right? Because this is a range chart. And you told me, well, if I want to compare between groups, I better use averages, right? Ooh, this is an averages chart, so there's between groups. But I need some way to compare them to each other across the 2 charts. And if I just have an averages chart and a range chart, I don't have a way to compare to each other. Or do I? Dun, dun, dun. I do, because I took the range on average from here and I tossed it into a formula and made those red bars. So those red bars on the top, They came from this range chart, so they represent the within variation. That's the punchline. That's it. No more, everybody. That's it. So the red bars represent the within variation. Okay? The points represent the between. So what's bigger here? The red bars or the points? The averages on the top chart. The red bars are the points. This is how we can mathematically compare between and within. The distance between those two red bars is right there. The distance between the lowest of the low points is right there and the highest of the high. So I can make a comparison, and that's what we can do here. I'll show you some examples. Oh, I just talked through all this, so I can sort of skip over it. So those lines become the water lines. There it is visually. Between is these guys, and within is the red bars because it came from the range chart. What's bigger? In this case, between. Right? I'm just following what you told me. You told me ranges, which generate these red lines, represent within, and points, these averages, represent between. I'm just making a comparison. Okay? So I'm using the control chart in a different way than I did before. So now let me give you scenarios here. This green scenario, we don't have any instabilities. We have a pretty trustworthy process down here. What's bigger, the width of the red lines or the width of the points? So what's bigger, within or between? So what would I work here? My different colored marker lines or within any marker line? Different colored lines. I try to figure out how they're different. And I might go, let's say this was a purple line and this was a blue line. I say, why is purple and blue so different? Okay? I can ask those questions now. Let me skip that one and show you this scenario down here. Skip the middle one. We're going to the bottom scenario. Looks nice here, no instabilities. I come up here, my red lines, it's hard to see. They're way out here. The points are a lot more clustered, closer to the inside. So what's bigger now? The difference between production lines, the points, or the control limits, the within? The control limits within. Now, here's the trick scenario. Looks good on this chart here in the middle. I come up here, my red lines, top one's there, my bottom one's there. I have points that almost span the same distance. What's bigger, within or between? Hint, it's a trick. About the same. So I haven't found the production line versus the within production line is not a good splitting variable in this case. I need to look elsewhere. Maybe it's shift to shift or plastic batch to plastic batch or something else I can divide on. You guys with me? Good. All right, so all this shows you is what the answers are, and you gave me the answer. Between is greater than within. They're about the same. Within is greater between in this scenario. So I can label that sort of like that. Between is greater within, between is about the same, and within is greater than between. So what I thought I'd do real quickly is show you this with some real data. And the scenario is, this is Minitab, so I wanted to get you some semblance of what's going on in Minitab. I have a data sheet here. And what I have is a column of cartoon dog. And what BHP has decided to do, this is in the works. I don't know if you're going to believe me. It's not really in the works. But this is in the works. We're going to select a cartoon character for our marketing campaigns. And it's going to be one of these dogs. Astro from the Jetsons, Scooby, Snoopy, and Goofy. Everybody familiar with those 4 dogs? So we got to pay for those dogs. There's licensing fees and everything. So our public relations company has gone out and surveyed people. And I'm going to give you 4 different scenarios. They're different alternate universes, okay? So in scenario 1, they said, here, on this scale, tell us how much you like Astro. And they surveyed, they looked at how many rows of data? 6 people. And Scooby, same thing. And people rated their likability on some scale. Looks like it might go 0 to 30 or something. I can't quite tell. But they had a defined scale. And so trusting the measurement system, let's pretend it's good. I can go into Minitab and go do this. I'm just going to show real quick here, stat, control charts, subgroups, XBAR R. I want to show you how quick Minitab is. I can literally make a control chart in probably under a second. That's not an exaggeration. I can come in, I put in my variable that I want to look at, and in this case, my subgroup is this cartoon dog. And actually, what I'm going to do is label the scales with the cartoon dog so we don't have to figure out what's going on. And in this scenario, so it looks like there's different red lines here. So there must have been different amounts of people surveyed in each group. So if the subgroup size changes, the constant in that formula changes, that means the limits change a little bit. But my analysis approach does not change at all. The analytic method stays the same. So what do you see here? Does it matter which cartoon dog we pick? Which cartoon dog would you pick? So this is a higher likability score going up. So who do we like the most? Snoopy on average, we like it like, I don't know, 18. But what we're able to say here, we got a stable process. They all vary about the same within group. We do have between group variation. It looks like a lot of people dislike Scooby. I'm not sure if dislike, they don't like Scooby as much, and they like Snoopy a lot more. Fair? And that's real differences because the amount of variation within the group is the red lines. The points are outside. They're between variation. So let me go to a different alternate universe. Or maybe it's a different year we're doing this same survey. So, whoa, didn't mean to do that. So what I'm going to do is do scenario 2 here. Different alternate universe. And we have some public relation guys, you know, he's pushing, he says Scooby's my best dog. But Scooby costs about twice as much. Should we go after Scooby? I got some yes, some no. On average, Scooby is higher than everybody else, but we got a major problem here. There is a difference, but it's not a real and meaningful difference. The within variation inside each group, the likability of the dog inside, these red lines, varies much more than the between the variation shown by the group itself. So I would argue it doesn't matter what dog you use in your marketing campaign. There's likability issues with all of them. So there's variation issues inside each dog as well. So if Scooby costs twice as much as Snoopy, this is not a real and meaningful difference. I might go for the cheaper dog. Some people are shaking their head yes. Others are going, what the hell is he saying? All right, let me give you another scenario. Yes, there you go. Make your own dog. Who's Rex? Is that a... That sounds like an ExxonMobil dog. That's why I was asking. All right, so I'm going to go back and Control E. I'm going to do my scenario 3. See if we get any different alternate universe here. We get this data. What would you do? Okay, so Todd says there's a problem with the data within Snoopy here. And he's seeing that because this is my bottom chart here. It was the moving range yesterday. Today it's the range chart. But it's got a larger than expected range variation for Snoopy. Does everybody see that? I'm supposed to point for the recording for this column here. It's an unexpected variation. So we can ask, why does Snoopy vary so much? And we might do an additional subdivision. Maybe older individuals are really liking Snoopy, and younger individuals don't know who the heck he is. I don't know. I'm just making stuff up, right? But so there could be something, but I have a higher than expected variation here Therefore, I can't even trust this upper chart. I want to dig into this. So this sort of gives me something to go after this whole thing. All right, one more. Scenario 4. What do you see here? This is a trick one. I'm sorry for doing this to you. So do we have any issues down here? Everything's inside the red lines.
Don't like Snoopy.
Yeah, it feels like they don't like Snoopy, but it also feels like the within variation is pretty big comparatively. So I might be questioning whether dogs are any different. I would stay away from Snoopy, and I might do another analysis on the remainder of the dogs, Astro, Scooby, and Goofy, or try to dig deeper.
People don't like Scooby, and they see Scooby outdoors, they rate it higher. In this case, it's like Scooby and there is a...
Yeah, so how they were surveyed. So again, if we look at if we open the paper, has anybody got one of the big papers from yesterday? I was hoping everybody brought those back. And there's a stack at the end of one of the tables, so if anybody needs one. If we look at this chart, I like how you guys keep coming back to this left-hand side of the chart. This left-hand side of the chart is, you know, do we trust the data, the process, the measurement? And so if we don't trust how this survey data was taken, or do we even understand the process in which it was taken, so there's a lot of stuff on this left-hand side that we're not going to cover in this analytics class that is almost as important as everything we're doing in here, if not more important. So I like that kind of mindset. So a lot of the scenarios I'm going to show you today, you just got to pretend we trust the data, even though we may not. Okay, so now, the next thing I want to show you is talk about something called ANOVA. And we're going to throw in some hypothesis testing here. So ANOVA is a great analogy in the physical world, is this engine or motor sort of concept. So if you think about engines or motors, they're everywhere. Name some things engines are in. Cars, lawnmowers. That's it? You guys are done? That's all we got? Generators, locomotives. Let's pick something for this row. Anything else? Weed eaters. Oh, thank you, Alex. Any others? Blenders. Good. So we you know, they could be electric motors, could be internal combustion engine, but there's motors everywhere, right? We can even go to the turbine engine realm. So most of the time they're hidden from sight, but they're very powerful for us, right? They do a lot of work for us. ANOVA is very much like that. It's everywhere. If you're doing regression, there's ANOVA under there. If you're doing design experiments, there's ANOVA under there. If you're doing some kind of measurement system analysis or components of variation analysis, there's ANOVA under there. There's many different types of ANOVA that I'm going to go through in a minute. So it's everywhere in the statistics world. And so it stands for analysis of variance. Analysis of variance. And so what we're doing there is comparing means, even though it sounds like we're comparing variation, but we're comparing means in the context of variation. And so I think I covered all that. Oh, here it is. ANOVA can handle simple situations, and I'm going to show you some of those, all the way to very complex multi-mix models with interactions, general linear models, very, very complex scenarios. And you have to get pretty smart to know how to implement these general linear models. So now, again, you guys ready for more animation? Yeah. Okay, so eyes on the screen. Here we go. Seat belts if you have them. All right, so here we have some strength versus temperature. And so we have 5 different temperatures it looks like we tested at, and we evaluated strength of something. I don't know, some kind of glue maybe or something. Okay, so what's your analysis of this data? Does temperature matter? Is temperature the only factor? Probably not. Okay, good. I like that analysis. Let's decompose this sort of visually. I can take this data and push it with a bulldozer to the right and get a distribution. You guys could do that, right? Take your hand, sweep it over, becomes a distribution. Okay? I could then take that data and there's the sort of the width of the distribution. That's the overall variation. I could take, forgot that. I could take this data and I could remove out sort of the temperature effect. So I'm sort of moving all the averages to a line. You guys could do that, right? Calculate the averages and then realign the data. I still have the variation at each different temperature here. And I could plow that data over into if distribution. It turns out it's the same width, but that's the within group variation. You guys agree? I could do one more thing. I can take that distribution one more time, and I could get the average of each group. That's the pink dot there. And now I could look at the width of that variability there, and that's the between group variation. Does this seem familiar? Didn't it? This is like almost the same thing I gave you a little bit ago, isn't it? Turns out where the X bar R charts are sort of the graphical way to do this, ANOVA is going to be the analytic way to do it. So we're going to use numbers and hypothesis tests. And so, oh wait, we got to do that again. You guys ready? Everybody watching the screen? Look at that. So what we're showing here is the within group variation, but plus the between group variation is the overall variation. And we can use this mathematical formula in ANOVA analysis, and that's what we do. It's pretty simple. Yes?
Why would you use a root mean square?
A root mean square. So what's your context there?
So in looking at variation, right? So I can take groups of data, and I can square each one.
So
Take the average and then square root that.
Okay, so when you say root mean square, what I believe you're talking about is a statistical property that shows up everywhere called sum of squares. So when we're using ANOVA, we have sum of squares. When we're using components of variation, when we're using regression, the sum of squares shows up over and over and over again. Even calculating the standard deviation, we have. So I think standard deviation formula you just gave me there was the square root of the differences from the mean squared over the population side, or the population size minus 1. That's the standard deviation.
Right, but so there's two means, right? I can get a mean where I just add all the variables up,
Mm-hmm.
divided by the number of variables.
So that's what we're going to do with this overall. Mm-hmm.
Or I can square each variable.
Okay.
Sum them.
Okay.
Divided by the number, and square root that. Now I get the square root of the sum of the squares.
Okay, yeah. So that's working in most statistical calculations. It's sum of squares. And what we're doing is components of variation don't sum. We have to sum variances, which are standard deviation squared. So let's take that offline. I'll dive into that a little bit deeper. But that's the underlying math that's happening here. Yeah.
Variation plus the overall.
Right.
Calculated between using average, the overall.
Yeah. So this is a rough visual. The actual math is that sum of squares, and we're doing components of variation. So this is sort of this equation is a little bit conceptual here, right? We're taking some representation of the within group variation and some representation of the between group variation, and that equals overall variation. And what we're going to do with statistics, all hypothesis tests are some kind of comparison of between over within. That was when I learned statistics the first time in college. I didn't quite unify it in my brain, but something happened maybe 15, 20 years ago for me where I realized all statistical tests are a comparison of between over within, signal over noise. Okay? So this is a very powerful concept, and I'll show you how to leverage that in a little bit. But so we're using this concept of between, over, within. So if I give you an example, if I have two runners and I tell them I want to time them running from here to the other side of this floor, we put safety, quarantine, whatever, don't worry about all that. We get them all lined up, time them, and I time them 5 times each. How do I determine who's the faster runner? I could just time them each once and decide who wins that, who's got the lowest time. What if I timed them 5 times? How do I determine who's the fastest runner? They look at an average. But what if there was high variability between each of those run times? Is the average maybe truly different? So I can illustrate that with a quick graphic. So vertical distance, again,